Welcome and thank you for downloading the SteerDuff podcast.
I know it's rather late today, but if you can just bear with me for 2 times 45 minutes. My name is Mark Voskel. This is the last part of the Introduction to Aerospace Engineering course. And what I will talk about is flight mechanics. And of course that's the most interesting part of the course, as we all think. But I'm sure you don't quite know yet what flight mechanics is about. So I'd like to start just with a question to get your minds going a little bit. Now imagine you're in that Boeing 747. If you can just be a little bit more quiet. Imagine you're in that Boeing 747, 10 kilometers altitude, so about cruise altitude. And for some reason whatsoever, all engines fail. Now, you may think that's a weird scenario, but it's happened before. It can happen due to 2 reasons. First reason being that the fuel runs out. Indeed. Another reason could be that maybe there's a volcanic ash cloud. It happened before in Indonesia that the Boeing 747 lost all engines. So the question is, are you still able to reach an airport and land safely without any engines operating? So I don't use turning point, so if you can just raise your hand if you think it's answer A. No? B? So fair few people think it's B. C? And D? Okay. Now, of course you want to know what the correct answer is. If you can just be a little bit more quiet. I've made a picture. This is if this happens above Amsterdam, then that circle, that's 180 kilometers. So answer D. That's what you can reach with this aircraft. So you can even fly almost to Brussels without engines operating. Now, to come back to the lecture, this is typically a thing you'd like to calculate if you talk about flight mechanics. So what I'm going to talk about this whole lecture is about aircraft performance, and those are things like how far can you glide, like in the previous example, how fast can you fly, how slow can you fly, how high can you go, or maybe if you want to fly from A to B, how much fuel do you actually need, or what's the furthest you can fly? So these are typical questions you should be able to answer at the end of my lectures, hopefully. And that's for a given aircraft, you can do these calculations. But I will also talk a little bit about aircraft morphology. I'm not sure if you know what it means, morphology. But morphology is more or less related to basically the shape of the aircraft. So if you know how far you can glide, then you can think of, well, what if I change my aircraft design slightly? Would I then be able to glide further or not? So aircraft design, so wingspan, etc., is really much related to aircraft performance. So that's aircraft morphology. So these are typical questions I'd like to answer, and it's important to realize that we try to analyze the performance of a complete vehicle. So it's not just aerodynamics, it's not just structures, it's not just propulsion. This deals with the whole vehicle, including the pilot, the atmosphere, and so on. So you can look at all these types of aircraft and do calculations about them. And then the next year there's a course on flight and orbital mechanics. Then you'll even start doing some calculations about orbits and space flight. I won't be telling you that because I don't know anything about space. So in this lecture series it will be only about aircraft. So we're trying to analyze the performance of the complete vehicle. And of course, if you want to know how far can it glide or fly, you have to be able to describe the motion of the aircraft as a whole. So this is why basically the center of my lecture series is about the equations of motion. So the equations of motion of an aircraft. So that's basically FSM times A. So this is what we're basically going to do. So it's not more than high school physics, really. But of course, the forces, they determine the acceleration of the aircraft and thus the motion. So you have to be able to understand all the forces that act on the aircraft. This includes propulsion, aerodynamics, the aircraft structure, in the sense that the aircraft structure will have a certain weight. And you can imagine that maybe a heavy aircraft might perform less good than a not so heavy aircraft. The pilot has an influence. Of course, the pilot can decide, am I going to fly high in the atmosphere or low, or what kind of strategy is the pilot actually doing? So this will also influence the performance. And finally, the atmosphere. Of course, at high altitude or low altitude, you have different air density, different temperature, and these parameters affect the equations of motion and thus the performance of the vehicle. So this is more or less what this whole lecture series is about. So hopefully you know now what flight mechanics is, more or less. And before I go into details of this course, just some practical matters like what book do you need, which chapters do you need to learn. And after that I'm going to treat three things basically. The general equations of motion. So point number 3, that's what you really should be able to do after this lecture. Points 4 and 5, propulsion and aerodynamics. They partly cover what you already know a little bit, but I'm going to extract what you know already to be able to apply it to the equations of motion. Finally, a summary and some additional stuff for the interested reader. So this is what I'm going to do. First lecture is more a general lecture, introduction, deriving equations of motion. And that's the tool really that we're going to use to solve all the questions that we may pose. After that, I'm going to look at horizontal flight performance. So performance questions like how slow, how fast can I fly, what's the maximum distance I can fly if I stay at a constant altitude. After that, it's going to be a little bit more involved. I'm going to treat climbing and descending flight, so the example I've just given, but also maybe if I want to climb to my cruise altitude, how fast, how much time does it take before I get there? And finally, fourth lecture is the flight envelope. And the flight envelope is basically a diagram which more or less looks like this, with altitude and airspeed, and there will be some region in this flight envelope where a certain aircraft can fly. So there will be maximum speed limits, maximum altitude, minimum speed limits. And within that region you can fly, and that's really important to the person that's operating the aircraft, because then you know what you can do with your aircraft. So this really tells you what the aircraft is able to do. Now clearly, airspeed and altitude, this flight envelope really depends on the altitude. So in the fourth lecture, I'm going to talk again about horizontal flight performance, again about climbing and descending flight, but I'm going to look at whether it makes sense to fly high in the atmosphere, or maybe it makes sense to fly a little bit lower in the atmosphere. And then finally, final lecture are just some questions and solutions that should help you for the exam. Now, what do you have to learn? You have to learn the lecture sheets if you understand the sheets that I show you in this lecture, then you know pretty much everything there is to know. There will be practice questions from previous exams on Blackboard, so you'll be able to look at them. If you use Introduction to Flight, it's those paragraphs listed there, but I have to say that not everything that I'm telling you here today and in the next lectures is in fact included in Introduction to Flight. In addition, I don't think Introduction to Flight is a very good book. Well, it's a good book if you're interested in aerodynamics, but considering this topic, it's not a really good book, and they use different notations than I do. So you can use it as background reading, but if you understand the sheets and you make some notes during this lecture, then you should have everything you need to know. There's also another book you could buy. It's only 14 euros. It's called Elements of Airplane Performance. It's not a waste of money because next year you'll need it anyway, so you might consider buying that. But that's up to you. Of course, everything I tell you will be put on Blackboard, but I will only put it on Blackboard after the lecture. So you have to wait for that. And there's no need to do any homework, so you can just come to the lecture and enjoy and pay attention, of course. But there's no need to really prepare you for these lectures. Just pay attention, that's the most important thing. So, general equations of motion, this is really the most important part of the lecture. So I'm going to derive equations of motion for an aircraft. And I'm going to do that in a couple of steps. I'm going to talk a little bit about Newton's laws, stuff you should really already know. I'm going to talk about coordinate systems. You can imagine if an aircraft is flying through the sky, then you need to define some axis systems to specify what the orientation of the plane is. Then I'm going to talk about some assumptions. We'll make some assumptions to make life a little bit easier. And then we'll derive equations of motion. So, now to start with Newton's laws, this equation really only holds when you're in an inertial frame of reference. And what does that mean? That's a frame of reference, so a coordinate system with axes, which is fixed in space and it's not moving at all. So it's completely at rest. Now, a coordinate system which is translating at a constant speed, you can prove that that's also an inertial frame of reference. And just to give you an example, let's say you were in a train and all the curtains are closed and the train is going at a constant speed, then, except for some vibrations maybe, you don't notice at all that you're moving. So you can jump in the train and you'll land in the same spot. So that's in fact an inertial frame of reference, and the equations of motion there hold. If, however, that train would go through, you still have the curtains closed, and you'd go through a corner, so circular motion, so a rotating axis system, then you'd notice something. You suddenly notice that you'll get squashed against a window, like when you're in a car, when you go around the corner. So you can see immediately that that case is not an inertial frame of reference. But that's an important observation, because an aircraft which may be pulling up is, of course, going around the corner. So in that case, the aircraft is not, an axis system fixed to an aircraft is not in an inertial frame of reference anymore. So this is the basics. And then for this picture, I would urge you to make a drawing. Now, if you look up, so take out your notebooks, I would say. If you would look up all the previous exams over the past 4 or 5 years that this course has been existing, or a couple of years, I think there's been 4 exams, then each and single exam, there was a question whether you could draw this. So, I don't know much about statistics, but there's a fair chance that it will be asked again. So, coordinate systems, there are various coordinate systems you can actually describe. Of course, one that's really relevant and obvious is an axis system which is fixed to the Earth, like here. So basically, this is what we call the Earth axis system. Out of convention, you can choose whatever direction the x-axis is located. Of course, it doesn't really matter a lot if the aircraft is flying in that direction or in that direction for your calculations. So the x-axis, you're free to choose which direction it is. The z-axis here is pointing to the center of the Earth. Now that's just that's just an agreement. You could have chosen it the other way. This is the way it is, and it's completely fixed. So this thing is fixed to the Earth, it's not moving. Now, of course, the plane is moving around. So you could also say, I take this axis system, this Earth axis system, I take the same orientation as the one fixed to the Earth, but now I fix it to the plane. So this is what we call a moving Earth axis system. So it's the same axis system, same orientation, it's just traveling along with the plane. And that's quite convenient. Now, once you have this, then of course you can imagine there will be other axis systems, because a plane is not always in a horizontal attitude. So what we can also define is what is called a body axis system. Now, body axis system is fixed to the plane, and the x-axis is pointing through the nose of the aircraft. So you can see straight away that there's an angle called theta. Let's see if this works. Oh. I'm not very good at these things. Well, doesn't work. So there's an angle theta between the moving Earth axis system and the body axis system. And the important thing to realize is that that's basically the angle between the nose of the aircraft and the horizon. So that means that the pilot, if he or she looks outside the window, is actually seeing that angle theta. So that's quite relevant from the pilot's perspective. Now again, the z-axis is just, why is that thing moving? The z-axis is just perpendicular to the x-axis. Then, of course, and this is quite important to realize, there is something called the airspeed vector. And that vector indicates in which direction the plane is going. And that's of course interesting, because that determines the performance, where you're going. And the most commonly made mistake is that you think that the airplane is following its nose. It isn't. This airplane, as it is oriented now, it could actually be dropping out of the sky like this. Then the airspeed vector would be pointing downwards. Now, that is typically not the case, but as you see here, this is more a typical case. The airspeed vector is in fact slightly lower than the body axis, which means that the airplane has an angle with respect to the airflow. And this is what we call the angle of attack, alpha. So, angle of attack depends on the airflow, what the plane feels, and the nose of the aircraft. So, if you would increase the nose of the aircraft with respect to the airspeed vector, then you'd get more lift. Finally, last but not least, is this angle gamma. And this is what we call the flight path angle. So the flight path angle gamma, that's the angle between the horizon and the airspeed vector. And it basically tells you how steep you're actually climbing or descending. So if you consider the case of the plane without engines, then the airspeed vector would be pointing down, and this will be minus the flight path angle, and of course that angle determines where you're going to land. So that's a really relevant angle. And then finally, we can define an axis system, which is called the air path axis system. And this axis system is in the same direction as the airspeed vector. So we basically have three axis systems fixed to the plane and three angles describing the differences between the three axis systems. Okay, so these are the coordinate systems we have. Now, these angles, theta is called pitch attitude, alpha is called angle of attack, and gamma is the flight path angle. And these angles, at least theta and gamma, they are called differently in the book Introduction to Flight. But all the other books use these notations, so that's why I'm using these as well. So that's to avoid confusion. Now we have all the relevant angles now. And before I start deriving these equations of motion, just a few assumptions I'd like to emphasize before I derive the equations of motion. Now the first one I assume is that the Earth is flat. Now you can see that if you would stay at a constant altitude, like so, then if you fly long enough, you're actually flying around in a circle around the Earth. Now, in order to achieve a circular motion, you need a centrifugal force. And what I'm going to assume is, I'm going to assume that the Earth is flat. And just a little calculation to show you that that is relevant. Now, the centrifugal force is basically this. mv squared over r. Now, if you look at the top equation, then in our case, m is actually the weight of the aircraft in newtons divided by the gravitational acceleration. V squared is simply how fast the plane is flying. And r, in this case, is the radius of the Earth plus the altitude of the plane above the Earth's surface. So this centrifugal force is what we call C. Now in the second equation here, I'm showing you the relation between centrifugal force and aircraft weight, because then I can express it kind of like a percentage. And if you know the percentage, then you can say whether it's a relevant assumption to neglect this. Now, just some numbers. This is an example. Now, V, 100 meters per second. You can calculate how many kilometers per hour it is, but it's approximately Mach 0.3, so it's fairly slowly flying. Radius of the Earth is given. Let's say we're at 0 meters altitude. And then you can see that in this case, C divided by W is 0.00016, so 0.016%. So that's really neglectable, and you can leave this out of the equation. Of course, if you would start flying really fast, like hypersonic flight, or maybe you start flying really high, so almost into space, then this isn't neglectable anymore. But the types of aircraft I'm talking about in this lecture, they fly up to 10 kilometers. They may fly supersonic, but not a whole lot. So this is really quite a good assumption. Now, another assumption that I'm making is that the Earth is basically not rotating. Because there are a couple of effects actually that happen if the Earth is rotating. And you can imagine if you are, let's say you're somewhere over here at the equator, and you would move upwards, then on the equator you're turning around quite fastly if you just stand. And if you walk along the Earth's surface toward the north, then that rotational speed becomes less. So it's kind of comparable to, let's say this would be, well, you know, one of these discos where you have a dancing floor that turns around. If you're in the center and this thing is rotating and you'd walk outside, then you'd feel that the speed is increasing and you'd feel force. So these forces are present if you consider the rotation of the Earth. So that is a relevant thing, and it's actually something you can actually measure. So I have an example here. If you ever go to Paris, there's this museum, and they have a really big pendulum. Now, the pendulum is actually located over here, so it's a big ball, and the cable is very long, so it doesn't fit in the picture. But the idea is that if you were, let's say, on the North Pole, if this is the Earth, and it's rotating around like this, and let's say you put some device here with a pendulum which is going back and forth, then as the Earth is rotating around, you would notice that if you wait long enough, you actually see what's on the right here. So these forces that appear because the Earth is actually rotating, you can actually measure them. And in fact, this is how they proved a while ago that the Earth was actually round. Now, it takes a long time. It takes a day before the whole cycle is complete. So you can imagine that these forces are quite small, and that we can actually neglect them now. But it is something you have to pay attention to next year if you start looking at orbital mechanics and spaceflight. Final assumption, I'm going to assume that gravitational acceleration is zero. Zero is constant. And that's in fact not completely true. If you go into space and a mass is further away from the Earth, you would notice the Earth to a lesser extent. So gravity is not constant, but if you consider normal aircraft flight up to say 80 kilometers, then gravitational acceleration is almost the same as at sea level. So that's, I think, a fairly relevant assumption. Final assumption I'm making is that I'm going to treat the aircraft like a point mass. I'm going to treat it like a little ball, basically, and I'm going to see what kind of motion it will make. So these are the basic assumptions. And now back to our equations of motion. So this is the picture I just made before. And what I'm going to do now is I'm going to make a free body diagram with all the forces, and a kinetic diagram with all the accelerations of the plane. Combining those will give us the equations of motion. So let's just list which kind of forces there actually are acting on the plane. Now, clearly there's an aircraft weight, and you can imagine aircraft weight is always pointing towards the center of the Earth. So that's in the same direction as this z-axis of the moving Earth axis system. So you can see straight away that these axis systems will become relevant right now. Now, aircraft weight, that's quite obvious, I guess. But now let's have a look at the lift factor. And lift is by definition always perpendicular to the airspeed factor. So that's something to pay attention to, because in most courses you just consider, say, horizontal flight, and then lift is pointing upwards. But you could imagine if you're flying straight up with a fighter aircraft, then lift is actually pointing in that way. So lift perpendicular to the airspeed, by definition. So it's in this air path axis system. So it's in the XA and ZA axis system. Now if you have lift, you always have drag, unfortunately, and drag is by definition perpendicular to lift and in the same but opposite direction as the airspeed vector. So that's pointing backwards. And in this case, since we're climbing, in fact, the airspeed vector is at a slight angle upwards, aerodynamic drag is actually pointing downwards a little bit. Then finally, we have a thrust vector. Of course, you have a propulsion system, and a propulsion system always creates a force, thrust, and that force doesn't necessarily have to be in the same direction as the nose of the plane. Just to give you a simple example, I don't know if you know this aircraft, but this is a tilt rotor aircraft, so it's kind of a mix between a helicopter and a propeller aircraft. But these big rotors, they can point upwards and forwards. But you can see straight away that in this case, the thrust vector may be in a completely different direction than the airspeed vector. So these are the forces that we have, and I've introduced one new angle over here, and that's called the angle of attack of the thrust vector. So the thrust vector has an angle with respect to the airspeed vector. So again, it's called alpha, but now since it's of the thrust, we call it alpha t. Now let's start writing down the equations of motion. So we're going to sum all the forces in two directions. Of course, a plane can move in two directions, or in two dimensions. So we're going to sum all the forces parallel to the airspeed vector. And now you may ask, why parallel to the airspeed vector? Why not just horizontal? If you take another direction, it's also fine. But if you take forces parallel to the airspeed vector, then that's convenient and you get simpler equations. So it just makes life a little bit easier. Now, the accelerations we don't know yet, but we can start looking at the forces. And you can see that the thrust vector has a component, a cosine component in the direction of the airspeed. So the cosine of this alpha t times the thrust vector, that's the component of the thrust in the direction of the airspeed. Now, drag is parallel to the airspeed, but in the opposite direction. So we have minus the drag. And the weight is in fact also pointing slightly backwards with respect to the airspeed vector. And I should really have drawn the ZA axis in between these two axes, because the ZA axis is perpendicular to the airspeed. So you can see, if you take the component of the weight parallel to the airspeed, you get minus the weight and the sine of the flight path angle, gamma. So these are all the forces parallel to the airspeed. Now, it can do the same thing, but then perpendicular to the airspeed. So the sum of the forces perpendicular to the airspeed vector, they are as follows. By definition, lift is perpendicular to airspeed. So we have lift. Now the weight is pointing downwards, and there's again this angle between the ZA axis and the moving Earth axis. So the weight component in this case is not the sine of gamma, but it's minus weight cosine of gamma. And since we have this thrust vector over here, thrust is actually pointing upwards a little bit. So we get plus t sine alpha t. Is there a question? Sorry? Well, that's just basically a historical thing. It's just something you can agree on. You could also define another axis system and say, okay, I'm going to put z-axis upwards. Would also work. Sorry? Well, yeah, I'm taking perpendicular to airspeed, and I'm saying upwards is positive, but you could do, if you do it the other way around, you just get minus signs in front of this. So, let's say it wasn't my choice, everybody in the world does it like this, so why am I the one to change it, I would say. This is just the way everybody does it. So you see, we have all the forces now. Before the break, we can have a look at the accelerations as well. So the same diagram, but now we're going to look at the accelerations of the aircraft. If you can just have your attention for a few more minutes. Yeah. There is, well, the y-axis is in fact pointing outside the board, but L is perpendicular to the airspeed vector. So maybe I it's basically like this. So by definition, it's okay. Then back to the accelerations, and we're almost at where we want to be. That's the equations of motion. So I've taken forces parallel and perpendicular to the airspeed. So I'm also going to take accelerations in these two directions. Now, you can say that the airspeed may increase or decrease with time. So you may have a change of airspeed with time in the direction of v. So that's a fairly simple acceleration. So if you would complete the equation of motion here, you'd have mass, so aircraft weight divided by gravity times dv dt. Now there may also be some kind of a vertical acceleration. And you know that if you have an acceleration perpendicular to the speed vector, then you will start to go in a circular motion. So basically, if you're in a car and you're driving straight and you make a force to the right, then you start to go in a turn to the right, really simply. So you can imagine that there may also be a vertical acceleration of the plane, and such a vertical acceleration will make the plane go in a circular motion like this. So imagine this is a circle, And this is the airspeed vector. We have this angle gamma. So if you're going in a circular motion like this, then you basically have a change of this angle gamma of the airspeed vector with the horizon with time. And you also know, because we're considering a circular motion, that this airspeed vector will be angular velocity multiplied with radius. Or sorry. So, yeah. Multiplied with radius. So, if you look at the vertical acceleration, then this may look a bit odd to you. I'm writing down v times d gamma dt. That may be a little bit strange. You think, where does that come from? But it's in fact the same as having v squared over r. In this case, you don't know what r is, so it's more convenient to work with this gamma. But you can see from circular motion there's a relation between change of flight path angle with time and the radius. So we have a vertical acceleration, and this finalizes my story about the equations of motion. So the equations of motion then become this. So we have a vertical acceleration times the mass, and then we end up with these two equations. So we have one plane, it's able to move in two directions, two-dimensional space. We're treating it basically like one mass which is moving around. So we end up with two equations of motion that describe what the aircraft is doing. So that's all for this hour. In the next hour, I'm going to look at what are actually all the forces in these equations and how do they behave. If you can all sit down in the back. I just concluded with two equations of motion. And as you can see, I just tried to get the pen working, but I was actually drawing on the other side of the screen, so I'm going to continue with the chalk. I got about 10 times the same question during the break, so before I continue, I want to make one thing clear. That's the following. If you're traveling in a circular motion, then the velocity is always tangent to this circular motion. Now, the angle you have here is gamma, flight path angle, with respect to the horizon. You cannot see it. Is this better? Can you still not see it? Is this thing in front of it? Or? Oh, then I'll do it here. So, if you're in circular motion, and you'd call this omega, so the angular velocity, and this the radius, then omega times r equals the speed. Now, in our case, this angle is called gamma, so omega is in fact change of gamma with time. So this means that omega r is in fact d gamma dt, R is V. And if you would look at the traditional centrifugal acceleration, which is mv squared over R, and I put this in the equation, so I replace one of the v's with d gamma dt R, I get R divided by R. So this is the same as mv d gamma dt. So I hope it's a bit clearer, but that's basically what you see on the left hand side in the second equation. So it's the centrifugal acceleration, but the only reason I write it down like this without the radius is because I already have a flight path angle in the equation, so I don't want to add another variable, which is the radius. So much for equations of motion. Now, you've seen in these equations of motion there are a couple of forces that are quite important. There's the thrust, there's the lift, drag, and the aircraft weight. Those are the four basic forces. Now, aircraft weight in the things I discuss is more or less constant. Of course, if you burn fuel, then an aircraft may become lighter. In fact, if you fly for 8 hours on the way to China, then aircraft weight might actually reduce by about 40%. But in this lecture, I'm not going to treat that. Most important forces to discuss are propulsion and aerodynamics. So these are the two topics I'd like to discuss in this hour. And what you see in these equations is I'm talking about real thrust, real drag, real lift. So not a lift coefficient, not a drag coefficient. I really want to know what these forces are. So I'm going to look at some equations you should already have seen in this lecture or in the previous lectures, Introduction to Aerospace Engineering. But I'm going to change them a little bit, and I'm going to highlight what you need for this lecture. So some of the things you've already seen, but it's just a little bit as a refresher and to change it to apply it in the equations of motion. So in terms of propulsion, I'll look at some fundamental equations and definitions. As you can see, there are many types of different engines. So you can see very big propellers. The one on the left here, the Blackbird, is actually a ramjet. And you have turbofan engines on civil aircraft. So very different engines. And I'm going to discuss, well, is the one better than the other or not? And how do we apply these engines in our equations of motion? So the most fundamental thing is to realize that if you have a propulsion system, then no matter which one you have, they all work in the same way. They all somehow take a bit of air and they accelerate it. And by accelerating air, you create a force through the momentum equation. So basically the momentum of the mass flow of the air at the exit of the engine compared to the momentum at the entrance, the difference between the two, that will be actually the force that is created. And one important thing in this sheet is that when I talk about mass here, it's actually a mass flow. So the units here are kilograms per second. So I could have put a dot on top of it, but it's a mass flow. I is the, well, maybe in Dutch you'd call it impulse, but in English it's the momentum. So it's also impulse? Okay, well. So it's mass flow multiplied with V. So momentum would be mass times v, and derivative with time is then what you have here. So at the exit of the engine, you have a mass flow of the air that's going through the engine. There's a mass flow, a little bit extra mass in there, mf, because we have fuel, we're burning fuel, and that goes into the air. That gets multiplied with Vj, which is the jet velocity. And if you subtract the mass flow before it enters the engine, multiplied with the airspeed, so V or V0 in this case, then you get the actual thrust of the engine. Now, you can imagine that the amount of fuel that goes into the air is relatively small. So this term mf there is something we can neglect, more or less. So we can say the thrust you create is in fact this mass flow multiplied with the change in velocity at the exit and the entrance of the engine. So two variables you have really, because V0 is the speed at which you're flying. So if you design a propulsion system, you can play with this jet velocity or with the mass flow of the air. So basically you have two options in order to create the same amount of thrust. You could say, okay, I take a little bit of air and I accelerate it a lot. Then you would be playing with this jet velocity. Whereas you could also say, I'm not going to do that. I'm actually going to take a lot of air and give it a little push, and you get the same amount of thrust. So you can do two things. Take a lot of mass, little acceleration, or a little mass, a large acceleration, or anything in between. And that's really the difference between all these types of propulsion systems. So that's important to keep in the back of your head. Now, just to give you some examples, on the top here you see a propeller with a simple combustion engine like you have in general aviation aircraft. And that propeller is actually accelerating a large mass of air just a little bit. If you compare that to a jet engine, you know a jet engine makes a lot of noise, and that's basically because the air at the exit has a very large velocity. So a jet engine gives a very large acceleration to the air, and the air then is relatively small, or a small mass. And finally, not really the topic of this lecture, but you could also take the mass with you in a rocket, and then you can also create a force. So, if you look back at the equation, then for the propeller you have large mass flow, small speed difference, and for the jet you have a small mass flow and a relatively large speed difference. But then you might wonder, okay, which propulsion type is actually the best? Propeller, maybe a pure jet like you have on fighter aircraft, maybe a turbofan, which is a bit in between a pure jet and a propeller like you see in civil aircraft, maybe a ramjet, that's more a special case, or a rocket. But before you can answer that question, you have to say, okay, if you want to define what's best, we have to define what do I mean with best? Do I mean a lot of thrust or very efficient engine? So we have to make some definitions first before we can compare different types of engines. So we're going to look at three definitions. We're going to look at power, so basically energy per second. So power, and we're going to look at efficiency, which we express in terms of a percentage. We're going to look at a couple of powers, and I think 2 out of the 3 you've already seen, and a couple of efficiencies. And with these efficiencies, we'll be able to compare different engines. Now, power available is fairly straightforward. What you typically want to do with an aircraft is you want to fly from A to B, right? So At time t, you might be on the left there, and time delta t, you might be a little bit further. Of course, you have a thrust force in order to get there, and you travel over a distance delta x. Now, if you look at the amount of energy that it takes to get from A to B, then you have to, there's something which is called work, and which is basically a force times the distance is work, which is energy. So the force in this case is thrust. The distance is this delta x, or x2 minus x1, and that's the energy you need to go from A to B. Now, I'm not really interested in the energy. I want to know what is the power that I need. And power is energy per second. Was it a bit too loud? Or I can talk softly as well. So, energy per second. Very simple. Power then is work divided, so energy divided by the amount of time that it takes. Now, you have thrust times delta x, which is the work, the energy. You have time delta t, and you can see straight away delta x over delta t. If you make the delta small enough, you'll get the change of distance with time, which is airspeed. So, this power is what we call power available, but because it allows us to go from A to B, the power you have for transportation. So this is the most interesting thing. So power available is thrust times velocity. Of course, there are some other powers you can define, because you remember we're accelerating mass in order to get a thrust force. So you can imagine that there is a change in the kinetic energy of the air. So we can also define something which is called jet power, and that's basically the change of kinetic energy of the flow. Right? So if you look at the front of the engine, then kinetic energy would be half mv squared, and at the end of the engine it will be half mvj squared. Now, as I said before in my story, m is kilograms per second, so m there is a mass flow, so that's basically energy per second you see there. So it's a change of kinetic energy per second. Pretty straightforward, and that's what we call jet power. Now that's an important one, because you can imagine that after the plane has passed, the air is moving backwards. You've accelerated it, so you're losing energy in the air, and that will basically affect the performance. Was there a question? You can use, yeah, still working. Was there a question? No? Now, of course, I've talked about jet power, so energy left in the air. I've talked about power to go from A to B. That's the interesting part for the person flying it. But of course, this energy has to come from somewhere. And it comes, of course, from the fuel, from burning fuel. So the final power, the third one we can define, is called thermal power. Now, if you look at the top equation, then Q, which we call thermal power, is mass flow of the fuel, so kilograms of fuel per second, multiplied with H. Now, H is the heating value of fuel, and it's just a constant. It just tells you that if you buy a liter of fuel, how much energy is inside it. So it's kind of a chemical quantity, which is a constant value. It's just a number. So mass flow of fuel multiplied with this constant value H gives you the thermal power you put into the system in order to transport. Now, since mass flow is in kilograms per second, you can also define it with what we call, well, the mouse isn't working either, fuel flow, F, and fuel flow is in fact newtons per second. So if you look at the bottom equation, you have fuel flow over gravity. That's basically the mass flow of the fuel multiplied with this chemical quantity of the fuel. That gives you the thermal power. So all this says is if you open the fuel flow, you give more thrust in the cockpit, you'll use more thermal power. Yes? Yeah, that's actually not really relevant for this lecture, but M in the third equation is the mass flow of the outside air. So you could also say that all the energy of the fuel is transferred into the mass of the outside air. So it's basically heating the air. Q in is then the energy that goes into that air. So you can imagine that if you've flown a certain while, you also heat up the atmosphere simply by warming up the air. But now let's have a look at efficiency. And I'm going to define total efficiency as power available divided by thermal power. Because power available is that power related from flying from A to B, and Q, thermal power, is basically the amount of fuel you need. So this total efficiency just tells you, okay, if I go from A to B, I need a certain amount of fuel. And it tells you how efficient you transfer the fuel into transportation. Now, you can understand that if you take jet power divided by jet power, that's equal to 1. So in the second equation, I've multiplied total efficiency with 1, jet power divided by jet power, and then I've rewritten it slightly. So power available divided by jet power multiplied with jet power divided by thermal power. And if I do that, then I can make a distinction in efficiency. I can say, well, total efficiency is then power available divided by jet power, which is something we call propulsive efficiency, multiplied with jet power divided by thermal power, and that's what we call thermal efficiency. So I just made a distinction between two efficiencies. So total efficiency is a multiplication of thermal efficiency and thermal efficiency. Sorry? So eta J is propulsive efficiency and eta TH is thermal efficiency. But now let's have a bit of a closer look. If I can have your attention for a minute. Let's have a closer look at this propulsive efficiency. Okay? So this propulsive efficiency we defined as power available divided by jet power, right? As we see here. Now, we already know power available is thrust multiplied with velocity, and jet power is a half mvj squared minus a half m v squared. So that was that change in kinetic energy. Now, we already have an equation for the thrust, because thrust is mass times Vj minus V. And then of course we still have this V here. So multiplied with V. Now there's a half m here in both sides, so I can say divide by half m. And then I can say Vj squared minus V squared. That's actually the same as saying Vj minus V and Vj plus V. So you can check it if you work it out. This is Vj squared minus V squared. Now, clearly, these masses disappear. Now I have here Vj minus V, Vj minus V. So these two terms disappear. So I end up with thermal efficiency being, I hope it's readable, 2V divided by this Vj plus V, and I can also write this as 2 divided by 1 plus Vj over V. So in this final step, I'm dividing the top and the bottom by V. So this is an expression for the propulsive efficiency. So it's just a function of jet velocity and the speed at which the aircraft is flying. Okay? Now, if you take that equation, then if Vj is equal to V, then you would find that propulsive efficiency is 1, which is 100%, which is good. But, of course, thrust is basically mass flow times the change in velocity. So if you start creating thrust, the jet velocity will be higher than the airspeed, and therefore this eta j, which depends on these two terms, will always be smaller than 1. So in order to transport yourself, you have to accelerate air, which means you leave energy in the air, which means the efficiency of your system is always smaller than 100%. So you cannot transfer all the fuel energy into transportation because you leave energy in the atmosphere. So if you look at this, then you see this efficiency is actually dropping as the ratio between jet velocity and airspeed becomes larger. So a large acceleration of the mass leads to a lower efficiency. And this is something you can actually use to look at, to compare different propulsion systems. So what I'm going to compare are propeller aircraft and jet aircraft. Now this example, if you can just be a little bit more quiet in the back. In this example, I'm going to create 100 newtons of thrust, but I'm creating it at two different airspeeds. So in option 1, I'm flying 200 meters per second, and in option 2, I'm flying 300 meters per second. Now I say let's keep the mass flow the same. 1 kilogram of air per second goes through the engine. I'm giving the air the same acceleration, so an increase of 100 meters per second, and in both cases I get 100 newtons of thrust. But you can see immediately that the thrust is identical in both cases, but this ratio of Vj over V is not the same. because in one case it's basically 200 divided by 100, which is 2. In the second case it's 300 divided by 200, which is 1.5. So you can see that if you look at the first option, then the propulsive efficiency, if you type in the numbers, is only 66%. And in the second option, propulsive efficiency is in fact 80%. So if you give the same acceleration to a bit of air at a higher airspeed, second option, you end up with a better efficiency. So that's maybe a little bit curious, but this means if you fly faster, it makes sense to accelerate the air because you get more efficient. So this is why if you look back at this equation, thrust is mass flow times the speed increase. And as said in the beginning, you can do two things. You can take a large portion of air, give it this little push, or a small portion of air and a large push. Actually, if you fly fast, it makes sense to play with this acceleration. So if you fly fast, a thing like a jet engine becomes more efficient. And this is why you see that the question whether you need a jet or a propeller isn't worse than a jet. In fact, even though it may look older, a propeller is better at lower speeds and a jet engine is better at higher speeds. So basically for each speed at which you're flying, there is a certain propulsion system which is most efficient. So at low speeds you might want to use a propeller. At high speeds you might want to use a jet. And at even higher speeds you might want to start using things like a rocket or a ramjet or other exotic propulsion types. So there is no answer to the question, and this is just a summary of the equations you've just seen. Now, don't really try to memorize them. I don't think I will ask them either on the exam, but we'll need this to understand a little bit more about the propulsion systems. But what I talked about so far is I talked about propulsion systems in general, but let's now have a look at two different types of propulsion systems and how they actually behave. So we have a jet engine, which is one case I'm going to treat, and a propeller engine is the other option. And a jet engine more or less works like this. Air comes in at the left-hand side, and this air is actually standing still and the engine is moving. But in this picture the engine is of course still. So air comes in and then it sees this engine, so it gradually has to reduce the speed, and when it does so it compresses a little bit. So the pressure increases a little bit in front of the engine. Then it's going inside the first bit, which is a compressor. So these green discs, actually one green disc is rotating and the next disc is standing still, and then another one is rotating again. And what this thing is doing is it's putting energy into the air and then stopping it again. And by doing so, it increases the pressure of the air. So how it exactly works at this moment is not so important. What's important to realize that after the compressor, the air pressure has increased by maybe a factor 30. So you started with atmospheric pressure, then you had a little pressure increase because the air hit the engine, and then inside the compressor the pressure increases a lot. Then after the compressor, fuel is injected into the engine. It's then ignited, and of course you have now a high pressure gas which is very, very warm because you just combusted the kerosene. And of course that gas wants to expand. You know, it's very hot, very high pressure. Now the turbine is basically a thing which is more or less, it's connected to the compressor, and the air is trying to expand, and as it does so, it goes through the turbine. So it's a bit like a wind turbine. Air comes by and the thing starts to rotate. Now, because it starts to rotate, a part of the energy is extracted out of the air, and that rotation is used basically, I don't know why this doesn't work, but the turbine is basically used to drive the compressor. But since we put a lot of energy into the gas in terms of kerosene or fuel, there's still a lot of energy left after the air has passed through the turbine. And then, since there's still energy, it will accelerate when it exits the engine. It goes through the nozzle in order to make it expand nicely. And of course, the air there has a higher velocity than at the entrance, and the temperature is also higher. Now, just summarizing, at the intake I said, well, the air comes kind of to a standstill in front of the engine, and that makes the air pressure increase a little bit at the intake. But that compression at the intake is quite low. Maybe pressure increases by 50%, but it's really neglectable to what happens inside the engine. So inside the engine, the compressor makes the compression ratio up to a factor 30 or 40. And the jet velocity at the end is very high. Now, as you can see, this jet velocity really depends on what happens inside the engine, because there the air gets compressed a lot, and the engine doesn't really sense that much what happens in front of it. So if you would make thrust a function of airspeed, then it looks more or less like this. So you can see these lines. Let's just take one maximum continuous thrust, so that means you give full power in the cockpit. Then the thrust line as a function of airspeed, if you evaluate your engine at different airspeeds, doesn't really change that much. Of course, maybe if you go faster, there's a slightly different mass flow. Of course, this compression in front of the engine is a little bit different, but overall it's pretty much a straight line. You could make this diagram on the left for a lot of jet engines, and they all look more or less the same. So if you would take this thing on the left and you'd simplify it a little bit for our flight mechanics lecture, then what you can assume is that this thrust for a jet engine is more or less independent of airspeed. Of course, if you give more fuel flow in the cockpit, you get more thrust, and if you give less fuel flow in the cockpit, you get less thrust. But if you don't change anything, you just fly faster, you don't really notice it in terms of thrust. And this is a nice thing to have, because thrust is something we need in our equations of motion. Now that's jet engine. Then let's have a look at propeller aircraft. And basically what I want to do is, I want to end up with a similar graph like this, but then for propeller engines. And if we have those two, then we have the most important propulsion systems which we can apply in the flight mechanics. So this is what is called a turboprop, and a turboprop is the type of propeller you see on most civil aviation aircraft. So if you look on the right hand side, actually the whole engine part is the same as the jet engine. There's only one difference, and that is that instead of course, the turbine in the back is used to drive the compressor. So you have this high pressure gas in the combustion chamber which tries to expand. It's very warm. It goes through the turbine, but in a turboprop you actually have a little larger turbine. So instead of letting the air out at the end at a high velocity, you use that energy which is still left in the air actually to drive the propeller. So there's a shaft going to the propeller. There might be a gearbox to make the propeller rotate at the appropriate speed. But basically all the energy is used to drive the propeller instead of accelerating the air. So if you look at the airspeed at the intake of the gas turbine and at the exit, then they're more or less the same. But of course the propeller is rotating, and the propeller is the device that's actually accelerating the air and creating thrust. So, of course, what you would see then, if you consider a propeller, then in front of the propeller there's a certain airspeed, and since the propeller is rotating, it's actually accelerating the air backwards. But how does that actually work in detail? Now this is a picture you then have to look at for a couple of minutes maybe. But if you consider a propeller blade, then this is actually quite similar to an aircraft wing. If you make a cross section like it's done over there, then that cross section is in fact just an airfoil like on a wing. So if you look at that cross section, then it's actually traveling at a very high speed just because the propeller is rotating. So this cross section has a large speed due to the rotation. Now, of course, the propeller as a whole is also traveling forward, which is V0. So the cross section sees the combination of these two velocities. So omega r and v, together you get some kind of a total velocity. And the angle between the actual cross section and the total velocity is then the angle of attack of the blade section. And of course the angle with this horizon is what we call beta, and that's simply how you design the propeller. So that's a geometrical thing, that's an angle you've given the cross section. Now of course, because you have an angle of attack here, you get lift and you get drag. And that's very nice, of course, because the lift basically creates your forward thrust. And you more or less create lift by, if you look at a wing of an aircraft, and air flows by, then the wing actually pushes the air down. So this is how the propeller accelerates the air backwards. So what we see is air accelerates through the propeller. Is there a question? Yes. Good question. Yeah. The question is, does this blade have to have different geometry at the outside or the inside? It does, because you can see that this omega r, omega is how fast the propeller is rotating and r is the radius, then the angle of attack depends on the radius. So if you're at the tip of the blade, you have different r, so different angle of attack. So you see the propeller blades kind of are curved like this, in order to have the same angle of attack along the whole propeller. Skip this. One thing you have to be aware of is, I just need 2 more minutes I think. One thing you have to be aware of is that this picture I've drawn here isn't completely true, because the air is actually accelerated through the disc. So the airflow at the disc of the propeller is a bit higher than the actual airspeed of the vehicle. So if you make the full picture, and I don't say you have to do this yourself, this is just for information, then there is an additional velocity, Vi, which is because air is going a bit faster through the propeller, so this affects the angle of attack a little bit. But we don't really need that now. All we need to know is that the geometric angle of the profile affects basically the angle of attack of the local blade section, and therefore it affects the lift and the drag. So you can imagine that since the forward velocity also affects the angle of attack, then maybe if you fly faster, it would be nice if you could change the pitch or this angle of the blade. So what you see, I just need 1 more minute, so just be patient. If you see a propeller operating at takeoff, so no speed, then you could have a different attitude of the propeller compared to when you're flying forward in order to have the same angle of attack. So most propellers of turboprop planes, they can actually change the pitch of the blades during flight. So if they go faster, they change the blade angle. Maybe if they have an engine failure, you could put it such that it doesn't create that much drag, so you can glide well. And actually when you're landing, you could actually make reverse thrust with a propeller. So this is a nice feature. And because of this, if you make a picture of the efficiency of the propeller as a function of J, and J is basically it's basically a non-dimensional velocity of the plane. So if J is 2, you're flying faster than J is 1. And what I've shown here are efficiency curves for different angles of this propeller blade. So you can imagine that you get the best efficiency at a certain angle of attack, because then you have the best lift over drag ratio. And this efficiency occurs at a different speed for each blade setting. So what's nice now is that you can play with the blade setting as a function of airspeed to get maximum efficiency for each airspeed. So if you look at this efficiency curve and you change the blade pitch throughout flight, then you could achieve maximum efficiency. And this is why, and this is the final thing, this is why we can assume that for a propeller aircraft, since we can apply different blade pitches throughout the airspeed range, you can actually say that power available, which depends on this efficiency, is pretty much constant as a function of airspeed. So this is all I wanted to say about propulsion, and in the next lecture I'll tell you a little bit about aerodynamics.
Please visit our OpenCourseWare website for more information. See you at our next podcast.